All right, welcome back. EELE 101. It is week 5, and what we're going to do today is start looking at our first nonlinear device in this class, which is called the diode. And then we'll look at immediately the light emitting diode, or the LED, and get some experience with things that blink. Okay? All right, as we do this in lab, you are also going to have some experience with the diode. You're actually going to go into lab and you're going to build a little diode circuit using an LED, and you'll do some measurements on it, and we'll go through kind of how you might do that in class today. A note on the lab, there is a pre-lab. So if you take a look at this handout, what you'll see is we'll talk about these this new device we're going to have, a bunch of background, a bunch of cool stuff, but there's going to be a pre-lab in here where this will be the circuit that you're going to build, and you have to go through this table and calculate the voltage across the diode, voltage across the resistor, and the current for all these different source values. Okay? Now that, if you've never seen a diode before, that shouldn't make any sense to you, but after this class, you should be able to do this trivially. It's pretty simple. Okay? And then in recitation, you are going to do your last C experiment or exercise. So you're going to be working on functions, and it's the same thing as before. Watch a video, take a quiz, attempt the code, go to your recitation demo, print out your sheet, and then upload your code. Okay? Some of you have already done this. Let me ask you, how did it go today? Any issues? Nice. All right. To look into the future, you might be thinking, what are we going to do after we get rid of this putty and this text editor? Next week, you are going to start working on the Arduino single board computer. How many people have ever heard the term Arduino? Okay, it's very common. Okay, people have seen this before. You are going to purchase a robotics kit from our stockroom. Now this is in lieu of buying a textbook. We used to have you guys buy this really expensive textbook, and we said, this is stupid. Let's have them buy something that's meaningful, like a robot. So we have you buy this kit, and it's not cheap. It's like 185 bucks for EE students, and it's like $215 for non-EE. So it's about the same cost as like a big textbook. So apologies for that. The reason it's more or less expensive for EE students is you pay a College of Engineering fee, and so we offset that a little bit. So in the kit, you're going to have all sorts of parts. Don't start building the robot as soon as you see it and you notice where the wheels go and stuff like that. Don't work ahead on this yet. What we want to do is the next 2 weeks, week 6 and 7, you are going to get familiar with programming the Arduino computer just as if you were programming the EELE 101 server. So instead of typing your code and sending it over to some server in a different building, you're actually going to type up your code and you will send it to this little computer, and you'll communicate with this using a USB cable. So it'll be very similar to the way it's been done in the past. It's just that now this is your computer. And we want to all get on the same page in terms of the way we're developing, the way we're looking at the I/O coming out of this, the way we're able to do Hello World coming out of this thing before we start building up the actual robot. Then once you get to week 9, you will actually start building the thing and actually doing some exercises. And at that moment in time, in week 9, the lab and recitation will merge, and you will have 4 continuous hours each week just to work on Arduino-based robotics. Okay? All right, any questions or concerns about that? Okay, nothing? Have you thought about where to hold your hands? Yes?
Is it 185 for just electrical engineering or all?
For just College of Engineering. College of Engineering. So tell them, I'm an engineering student. No, 185. Okay? All right, has anybody thought about where to hold your hands? Nobody? Okay, I've got this new idea. It's to hold something in your hand. Okay? So we talked about when you're communicating, when you're presenting, it's always awkward where you put your hands, right? And some people do this. You don't want to do this because you cover up your heart. You can be distracting if you're just like talking like this. Well, if you have a problem with calming down your hands, a little trick is to hold something, such as a pen, maybe a laser pointer. You can click it. You can do stuff like this. But this is a good way just to calm yourself down a little bit and give yourself something to do. Because I don't know why, but does it feel weird when somebody talks like this and they just have their hands down? This is the way our arms were put on our body, right? Would you agree? but it is so unnatural to stand here like this and have your hands directly straight down. It doesn't make any sense. So the first thing you want to do is you want to like start bringing them up, and I don't know why you do this, and you start doing all this motion, and pretty soon you're flapping around and everybody's distracted. If you have a problem calming down your hands, grab a pen and just bring them on down, okay? I'm not talking like this, bring it down. I'm talking about right here, okay? Sound good? All right. What does this have to do with electrical engineering? Good answer. All right, off we go. Just really quick, the career fair is tomorrow. The career fair happens in the sub in the ballrooms, okay? It is a good time to be an engineer when you go to the career fair. It's always a good time to be an engineer at the career fair because most of the people that are over there are hiring engineers. And they're hiring engineers for everything, okay? They're hiring engineers to work for aerospace companies. They're hiring engineers to work at power companies. They're hiring engineers to do accounting software. They're hiring them to do anything and everything. And why do you think that is? Engineers are versatile, the best, humble, good-looking, smart. Come on, get out of here. There are needs that can only be filled by engineers, such as delivering electrical power to the universe. Okay, those are things that you're going to have to develop a skill to do. But you know what the biggest thing that you learn as an engineer? It's you learn how to learn in order to solve a problem. So you become problem-solving beasts by the time you get out of here. And it doesn't matter what the problem is. It's, oh, there's a problem. Let me learn about the problem. Let me learn about how other people have solved it. Now let me produce my own solutions to it and boom, solve the problem. So engineers become highly sought after because most people in the workforce are always solving problems. Okay, so that's why you'll see so many engineers hired in non-engineering, jobs. It is awesome to go to the career fair just to get an idea of all the people over there that hire from MSU. It's quite amazing to see, there's hundreds of companies over there, and they are begging people to come work for them. There's one company, there was a national lab. Has anybody ever heard of Los Alamos National Lab? They're pretty amazing. So in the, let's call it the aerospace kind of national lab, national defense type thing, there was this fear that everybody was going to retire about 10 years ago, and they said, we're going to have this huge workforce shortage, okay? There's not enough engineers to replace all the people that were retiring. The baby boomers, right? The boomers, they're all retiring. They've had it. And so then all of a sudden, the boomers were going to start retiring, right? This is about 10 years ago. What happened about 10 years ago that influenced the boomers? The recession happened. So the boomers said, you know what's better than retiring? Not retiring, because my house ain't worth anything, my 401k is nothing, so I'm just going to keep on working. So everybody just kept working. Well, now the baby boomers weren't going to, they're not people that are like 55 and retiring with this huge nest egg. They're more like 65, 70, so they're like, I don't even care if I have money. I don't want to work anymore. So they're all going to retire. Los Alamos National Lab, I heard this stat from a guy that's worked with them a bit. Last year, they had about 14,000 employees. They hired 1,000 people in 1 year. 1,000 people. And you know what their total company size went from? They started at 14,000. They ended at 14,000. Okay? That's how many people are actually retiring and leaving that particular organization. They could not hire, they were hiring like crazy just to stay flat. They were actually one of the organizations that they have actually given out job offers at the career fair. Okay? They're like, hey, how you doing? Resume? You're hired. You're like, whoa, dude, it's just here to get some M&Ms. But it is amazing how sought after you are when you walk through that. Go over there. I highly encourage you to walk around, get some stress balls, get the free pens. And actually, if you see somebody that's got something kind of cool, talk to them and understand what they're actually looking for. Another thing, this is free dinner week. Okay? Everybody's got these info sessions, right? Go out to the career fair website and you'll see these info sessions. Everybody's giving out pizza to get you to come and learn about their company, and they want you to come and just eat pizza and get free prizes. This is a week where if you're paying for a meal, you're doing something wrong, okay? So everybody get over there and just experience it. Yes? The career fair is 9 to 3. 9 to 3. Now, human beings tend to get tired. So I'm going to tell you, go over there early. Okay? At 3 o'clock, everybody is real angry. Okay, they're just like, oh my God, take the candy. I just get out of here. Go over there early. Try to get over there before noon, so where everybody's fresh and energetic. Then when you hand them, if you have a resume you want to give to them, then they're like, yeah, they write all over it. At the end, they're just like, get out of here. So, all right, any questions on that? What's that have to do with engineering? It is the point of this, isn't it? Okay, it's not just to satisfy some curiosity you had while you're watching TV one day. It's like, I wonder how that DVR works. Why don't I go spend 4 years in college and figure it out and then what? Get some lunch? No, it's about entering the workforce. You're here to gain some skills so that you can go and enter the workforce and build systems that benefit society. Okay? So this is your first step. All right. We are now going to talk about our first nonlinear device. Okay? And I'd like to start this off by drawing some cartoon pictures. Okay? First of all, we need to talk about something that's somewhat interesting. We talked about current being the flow of charge, right? Current is the flow of charge per time through a particular area. We have always talked about what is carrying that charge. It's electrons, okay? Technically, it's actually charge. Charge can actually exist other places other than just the electron. But in metals and conductors, what we typically do when we build circuits is we're moving electrons around, okay? Now, if I was to ask you a question like this, okay, if I had some sort of circuit and I drew a resistor right there and I said, which way is the current flowing? What would you say? Clockwise or counterclockwise? Yeah, we've been defined it as, okay, this is a passive element. Over here, this is an active element. The current in an active element flows from minus to plus and goes this way. So that's the current. If I asked you this, which direction is the electron flowing in that circuit, what would you say? It's actually counterclockwise, okay? So current is defined as the opposite direction as the electron flow, okay? So the electrons are actually flowing that way. You maybe have heard this story in physics, but where did this come from? Why did we guess wrong on this whole thing? It was that Benjamin Franklin guy, right? So he had all these experiments in the 1700s where he was like taking cat fur and glass and he's like, and he's sitting there and he's moving charge around and he's trying to figure out what was going on. And he basically came up with this concept in his mind of this electric fluid. So he knew there was stuff, but he didn't understand what it was. And he just happened to notice that when he flicked the fur over the glass rod, he would build up stuff over here, and then he would build like something over here. And he decided to define this thing in terms of like an excess of electric fluid and a deficiency of electric fluid. And he decided that the excess would be called positive and the deficiency would be called negative. So then years go by and people came along and started saying, well, but geez, could we use this to build circuits? And what is going to happen if we can move this charge around and like heat things up and create light? And so they defined that current would flow from positive to negative, okay? So that's the current flowing right there. And this was defined before they even understand what the electron is. Then comes along the guy that discovers the electron, and they started thinking about, well, the electron is really where the charge is, so when you build up the charge, is it an absence or is it an excess? And they discovered that the way that they defined this positive and negative with respect to current was actually the exact opposite of which way the electrons were moving once they discovered the electron. And they said, okay, the only way to make this make sense is that the electron is going to have a negative charge on it, and it is going to flow this way. And all it is a convention. It doesn't matter at all. We could have called it black or white. We could have called it yin and yang. It doesn't matter. It just happens to be that we have to assign the negative to the electron in order to get current as the definition of 1 coulomb per second traveling through a particular area. Okay? Now, the reason I say that is because we are going to now start looking at a device which is called the diode. Okay? And the diode in itself is pretty cool. It's a very nice thing. But it's the light-emitting diode that gets everybody excited, okay? So we'll talk about the theory of a diode, and then we'll move into the light-emitting diode. So to start off with a diode, what you want to do is you want to understand this thing that we call a p-n junction. And I'm going to draw this thing as a p-n junction. And we're going to draw some cartoons around this thing to try to describe how it works. You don't have to understand this right now. You don't have to understand any math associated with this. This is the conceptual model for how a p-n junction works. That then leads to the diode. That then leads to the light-emitting diode. And that ultimately leads toward the transistor, which changes everything. But we draw these cartoon models just to kind of build up, you know, an impression of how it works. Okay, so I come along and I say I have a p-type material. And the p-type material means that it has excess positive charge. Okay, so this is positive charge over here, and this over here, the negative, has an excess of negative charge. Now, all that really is in the atomic structure is that you've got like your nucleus and your proton of a material sitting here, and in the orbiting valences, the valence bands around these things, you just have an absence of electrons. So I'm going to draw like a little hole right here. And that just means that this material would accept an electron if you had it, right? So it's just a particular type of material or some compound that would accept electrons. Then you have over here this type of material that has a whole bunch of excess electrons. And if I drew this, you know, at the atomic level, what this would look like is it's just a material that has a whole bunch of electrons. So you'd have all these electrons cruising around, and they happen to be assigned this notation of negative, okay? This is possible to do. You actually take material, a material that can be easily changed by inserting impurities into it. This material that you can insert stuff into to change kind of its charge is called a semiconductor. Okay, you've heard of semiconductors such as silicon, right? So you take silicon, and what they do is that these companies that make these type of materials is they inject or they implant other materials that then give it this excess of positive charge or an excess of negative charge. And you actually create these materials. All right, this is how you make the integrated circuit. Okay? So you make these materials, and then what you do is you put them together and you see what happens. So somebody at some point, some engineer said, man, these materials are sweet. What would happen if we just jammed them together? Okay? I'm going to draw what the p-type material, I'll try to keep the p red. Okay? Try to keep that red over here. And we're gonna say it's positive, so I'm just going to draw some pluses in here. And I kind of want to keep this notion of, you know, I'm going to draw this little model up here of the nucleus, and I've got this orbiting valence that has a whole bunch of absence of electrons, okay? We just keep that model in our brain. Then here comes the negative side, and it's really got a whole bunch of negatives in here, and we're going to jam them together. And I want to keep in my head this notion of an atom that has all of these extra electrons kind of cruising, okay? So I come along and I stick these guys together. What is going to happen? You know, the whole rule is opposite charges do what? They attract. And similar charges do what? They repel each other, okay? So I stick this material together, and what do you think happens? These puppies go, oh, look, this is awesome. The negative charge starts cruising over here and goes, look it. There's a hole for me to jump into. So it kind of comes over to here, and they start migrating through. Okay, so they actually start going through here, going through here. And if you think about what happens, if I drew this again, this material is sitting here, and it's still got positive over here, life is good. These electrons are kind of forming or injecting themselves, or just kind of like trickling into these little holes right here. And what happens once they fill up all those little holes? The ion goes away. It's just now a satisfied atom, right? It doesn't have any charge anymore, okay? And so what happens is you actually have a region that is sitting in here that is not positive or negative, okay? Think about what happens over here on this side. Now we have this negative side, and you still have the negative puppies over here, and that life is good. And you think about what's happening right here. You're taking these atoms, and you're allowing the electron to migrate through the junction. So as these extra electrons kind of cruise over the junction, what ends up happening is that you're left with an atom that has an equal number of electrons and protons. So it doesn't have any charge anymore. So now all of a sudden you have a region over here which doesn't have any charge. And this actually is now what we call depleted of charge. So this is the depletion region. And this just naturally happens whenever you put a p and an n type material together. Okay? Now, here's the trick of this. No current will flow through this because current is basically charge that's flowing. So if you look at this, you've got like some positive here and some negative here, and then you just got like nothingness, right? So it's like, how would current ever flow through this? If you want current to flow, what you want to do is you want to have these electrons somehow get to a position where they can flow through this entire thing. So actually what we have to do to this, if we want current to flow through this junction, is we have to make this region go away. So we attach the material together and we go boom, and there it is. And it does that. We didn't even do anything. We haven't touched it. So then we come along and we want to use this to actually make current flow or run current through it. We have to actually come in here and apply a voltage to get this region to go together and disappear so that these electrons can suck all the way through the material and actually be current. Okay? All right. So you sit there and you go, well, how in the world am I going to do that? Well, let's think about what could happen if I came along and I applied a voltage to this fella. So now here I go. I got my voltage over here, 9-volter. And I'm going to take this and I want to propose to you that we do this. I want to take a positive and put it over here and a negative over here. Okay? No reason I had that battery up there. This is a negative over there. I want you to think about what's going to happen when I put a voltage across this. I have positive. Okay? What I'm going to do is it is going to attract what? What does the positive attract? Negative. Okay? This is a term. This is like a little, it's not a negative sign. It's like a lead or a piece of metal that we jam onto there. It is absolutely going to start pulling electrons. And the closest electrons to it are this little guy right here. So you got these electrons that happen to join into here and make this depleted region. All of a sudden, it's going to start pulling electrons out. Okay? So the electrons start moving that way. Now what happens as the electrons go away? This region then becomes positive again. So what happens is that that depletion region actually starts to shrink a little bit. Okay? Because these electrons are getting pulled over, and then the same thing happens over here where this now region gets a little bit smaller, and it's because these electrons keep getting pulled out of that little region right there as we have this voltage, and they're heading out of there, and then it keeps going and going and going. And ultimately, you will get to a situation where you have this. You have that same PN junction, except there is no depletion region. And these negatives right here and these positives right here, they are just hanging out, and you have a voltage now that's sitting right here across this PN junction, and you are taking these electrons and you're letting them flow this way. So these electrons are going, woo, baby. These electrons are going, woo, baby. These electrons are going, woo, baby. All of a sudden, it looks like a wire. Okay? Now, a whole lot of stuff has happened here. This is craziness. We took materials that were an anion and a cation, and we put them together, and a depletion region formed. And we said, if I want to use that thing, I have to apply a voltage to it to get current to go through it. But when I applied that voltage, it didn't start flowing right away. So if I put like 0.1 volts on that thing, what happens is the depletion region shrinks a little bit. And then I put like 0.2 on there, and it shrinks a little bit more, and a little bit more, and a little bit more. And I get up to like 0.5, 0.6, 0.7. Current's not flowing, okay? And all of a sudden you get to like, let's say 0.75, and all of a sudden, boom, the depletion region's gone, and all of a sudden electrons start flowing. So it's almost like, it's kind of like a switch. So you have this switch that is open, and you keep applying voltage to it, and at some point it will go, boop, and start allowing stuff to flow. That's the behavior of what we call a diode. So if I come along and I draw the symbol for a device that is going to look like this, it looks like this. Okay? So you put a triangle and you put a bar on it, and that right there is the symbol for a diode. Now, the current flows which way? We drew this cartoon model for the way that the device physics operates like this. But based on old Ben, which way is the current flowing based on this picture? Yeah, it's actually going that way because the current, our amps, is the opposite of electrons. So this model allows us to have this concept of what's actually going on at the atomic level. But we ain't going to make a living down there. we're going to come up one and we're going to go to that. We're going to abstract that thing and make this guy. This is the symbol for this p-n junction, and it has certain behavior. First of all, let's start by naming the terminals. This is no longer an unpolarized device. It matters which way you stick this in your circuit because the current is really only going to flow this way. Okay? So we are going to call this terminal right here the anode. Okay? And we're going to call this over here the cathode. And the reason is we want to differentiate ourselves from the cation material and the anion material. We're no longer at the material. We are at a device. This thing is a p-n junction inside a nice plastic that's got little leads coming out of it that we can attach to. We're a diode. We want to be related to the concept of anion and cation, but we're not right at the silicon level. We're up a level, so we're going to differentiate ourselves by saying the anode and the cathode. Sound good? So when we talk about the diode, that's where that terminology comes from, okay? All right, so I feel so good that I'm sitting here and I want to just think a little bit about how does the current flow through this if I was to take this and do something like this. I'm going to put a plus and a minus and a Vs, and I'm going to come over here and I'm going to draw myself a diode, and here we go. And I'm going to draw, this is going to be the current, we'll call it ID, and you know that it comes from over here, right? So it's basically this ID comes right there. And I'm going to draw this nice little plot. And what I want to do is I'm going to put Vs, okay, and we're going to sweep Vs from 0 up to something, and then we're going to look at ID, okay? Now, if you don't have any voltage, how much current would you think would flow? Nothing. There's no energy in the damn circuit. Okay? So you got nothing. So you're sitting right here and you got nothing. Now I start increasing Vs, which is the voltage across the diode. And what happens is that the current doesn't start flowing. This is kind of the weird part of it conceptually. If you think about our pictures that we had, when we put voltage on it, we were actually pulling electrons out, but we were doing it to close the depletion region, right? But electrons did come out, so technically a tiny, tiny, tiny bit of current was flowing. So really what happens is that you got this tiniest, tiniest, tiniest bit of current that's flowing, and then all of a sudden you get to the point where the depletion region closes, this thing becomes a wire, and it goes like this. Woo! It is a wire. Here is what is crazy about this. Okay? We have learned about our buddy, V equals IR. Okay? The wire has basically no resistance. Okay? It has no resistance. So what happens is it becomes, as the current goes through it like crazy, it becomes very difficult to develop a voltage across that because the current just flows like crazy. So you can't really figure out what the voltage is. So what we do is we say there is going to be some voltage where this thing just flips on and it goes absolutely nuts. This voltage at which it turns on, okay, where the depletion region vanishes, is called the forward voltage of a diode. So when you have a diode, you not only get to know what the anode and the cathode are, you also are given like its forward voltage. And so this will be a spec. A normal diode is like 0.7 volts. That's where you put enough voltage on it, all of a sudden current will start flowing. How's that feel? Okay, so life is good. Here is the equation for this current. So there's the equation for that current. That sucks, okay? I'm not going to lie to you. This is some exponential equation, okay, that has all these constants in it that are derived empirically by looking at the material, and it's going to basically model this perfect exponential curve that goes up like that. This is not a linear device. It's not linear because when you think about what linear means, linear is a linear expression that describes the voltage to current. V equals IR is linear. This is not linear. You know what else is horrible about this equation? Once you have stuff with exponents in it, you can't solve it algebraically. Okay? When you put this in a circuit and you start you do like KVL and KCL around it, and you try to solve it, you can't get to it algebraically. You just can't get the term down by itself so that you can solve for it. It's called has anybody ever heard of this, a transcendental equation? It's an equation that can't be solved algebraically. When you have something algebraic, you try to isolate the variable and solve for the number. You can't do it with this thing. You use a computer to try to guess and check on something like this, and this becomes very difficult. This leads us to this notion of what we call abstraction. Okay? Here is the reality. This diode, the equation that we use to describe the current through this, is too complicated to be useful. It really is. We have to come up with a model for how this behaves that we can understand. And what we call this is basically just the constant voltage model. Okay? So I'm going to call it the constant voltage model. And all this means is this. If V, we'll call it diode, and this is V plus or minus V diode, V diode is less than or equal to the forward voltage spec of the diode, okay, that little guy up there, then ID equals 0. Else, ID is greater than 0. Okay? We'll get that puppy right on there. Now here's what I want you to think about. So we've got this, we got pseudocode on here. We got it all, fellas. We got cartoon drawings of device physics. We have an exponential equation. We've got a circuit. We have some pseudocode. Might as well put that on there. There is electrical engineering in a nutshell, right? Here is what this means. You are going to increase the voltage of the source starting at 0, and no current will flow. As soon as the voltage gets up to the point where it meets this forward voltage spec of the device, this will turn on and current will flow. That's all that says. The second thing that's key with a diode is that the voltage across it clamps at that spec. Okay? That's what's great. That's the cool behavior of the diode. So all you got to do is say, here's a diode. I'm going to find out what its forward voltage spec is. And what I need is I need to increase the voltage at least up to that to get it to turn on. And then if I go above that, the voltage across the diode will never change. In this circuit, this is no good. But if I did have a circuit like this, which is usually what you have like a resistor and then a diode, what happens is that the voltage that doesn't develop across the diode will develop across the resistor. All right, how's that feeling? Whew. Yeah, it's pretty intense, isn't it? It's actually not so bad, okay? It just takes a while to get to the point where you're probably going, why don't you just say that in the beginning? It would have been a lot nicer than that little cartoon thingamajig. But guess what? Every class I teach, I draw that cartoon model. It doesn't even matter what it is. It'll be digital logic. Like, I didn't sign up for this. I'm like, I don't care. You're here. I'm going to draw this cartoon model. Because you have to see it over and over and over to the point where you're like, oh, now when you give me the math, which is in EE 409, you're like, oh, I get what the math is for. Okay? Nobody ever drew me this thing. If somebody would have drawn me this, college would have been so much easier. But no one drew me that. They just gave me equations. I said, you suck! So now I became a professor, and now I draw cartoons for a living. Okay. I say to you, let's use this thing in a circuit. First of all, you're like, I don't even believe a diode exists. Well, here's a diode. Okay? That's what a diode looks like. You know why it's important that that thing's got a mark on it? Does everybody see that mark? You got to know which one is the anode and the cathode. A diode has to have a and B terminal, an A and C terminal. You have to have it. Okay? Guess what? You know what a diode is called if it gives off light? A light emitting diode. So in this situation, if I was to come up to you and say, okay, I got this symbol for a diode. Okay, here's a symbol for a diode. Whoop, whoop. You got the anode and the cathode, and you're going, hey man, which one's the anode and the cathode? It's like this. So that's the anode and the cathode. So there's that. Then you go, I have an LED. You know what an LED is? It's just, when you look at this cartoon model right here, you know what's happening as you're moving stuff across this region? You are having electrons move into an orbital, then you're giving it energy to pull the electron off of the orbital. So you're giving it energy, and then you're yanking it off. You know what happens sometimes when you do that? It gives off photon energy. It gives off a photon. If that photon happens to be of a certain wavelength that we can see, light. Okay? It's always giving off photons. It's just that sometimes we can see it. So all an LED is a diode that gives off light. And the way we denote it is we draw a little picture of light. So you put like these little light arrows on there. And you're like, what's a diode look like? Well, here's what an LED looks like. So here's your LED. Okay, so this is a light emitting diode. LED, light emitting diode. And that's what it looks like. Notice that the pins, the legs of this thing, are longer and shorter. So this is the anode and that's the cathode. That's how you do it. Make sense? Okay. Why is an LED important? Light. It's pretty awesome, right? It's pretty awesome. What do we use LEDs for? Everything, right? Most importantly, we build TVs out of them, right? So all your flat screen TVs are built on LEDs. So you need different colors of LED. Obviously, you need a red, green, and a blue in order to make the nice pixel that's really small, and you can make all the cool images that you see. So you need different colors of LED. But the color doesn't come from the plastic around it. It comes from the wavelength of the photons that are given off when you recombine those electrons with the holes. Okay? How about your phone? Do you have LEDs in your phone? Yeah, you got your screen in there. How about that? There's LEDs everywhere. Look at it. I got an LED around my neck. It's flashing right now. They're everywhere. So, you say, would you please show me some circuits? Yes, I will. All right. I'll walk up to you, and I want to do the following. I'm going to put a circuit together, and I'm going to do something like this. This is a common circuit that we might ask you to solve. And I might come along and I might go plus or minus, we'll call it VS, and I'll go across like a, I don't know, 150 ohmer, and then we'll go through a diode, and I want to use an LED because they're awesome, so I write the LED thing in there. I need a specification. Someone needs to tell me that the forward voltage is 1.9 volts, okay? Normal diodes, the forward voltage is like 0.7. LEDs are about 2 volts, the stuff that we use. So this one happens to be 1.9 volts. A common question for this would be, when does it turn on? When does VS get the LED to turn on? Okay? Think about this. If VS is 0, is it on? No, there's no energy. What if VS is 1 volt? No. Here's what's interesting. If it's not on, there's no current. That's how it works. There's no current that goes through it. If VS was 1 volt, this isn't on, there's no current. There's no voltage here. There's no current flowing through the thing. What if VS was 1.9 volts? Oh! It turns out that this thing has now turned on. But there is no current flowing through it yet, because if this is 1.9 volts, this is also tracked was. Well, guess what? At the very instant that it turns on, how much voltage is left for our little resistor buddy? Nothing. The diode took all the voltage. And this guy has no volts across it. By V equals IR, how much current is flowing through the resistor? Nothing. So that's the transition. At the moment that the diode turns on, no current is flowing. Now, let us take this puppy up to 3 volts. How much, I got 3 volts here. How much voltage is across the diode? You have to remember the second behavior of the diode. It clamps at its forward voltage. It's on. The thing is on and conducting current. It is absolutely on. What is the voltage across the diode? It's 1.9. It just stays there. It's freaky. The thing just stays there. Well, what would tell us what the current is in this circuit? Ohm's law. Because if this is 1.9, what is left for our 150 ohm resistor? 1.1 volts. All the other voltage goes across there. Guess what? I can say V is equal to IR. I can say 1.1 volts is equal to the current times 150 ohms, and I can solve for the current flowing around that loop. That is how you dictate the current through the diode. The only way you can ever figure out what the current is by looking at other stuff in the circuit, because it's just a wire once it's on. So you always have a resistor in series with the diode to make it so that you can limit the current, okay? All right, let's take this puppy all the way up. You want to take it all the way up to 9 volts? Woo! Now, by this logic, I have how much voltage across the diode? 1.9. What is across the 150? Whatever's left, right? So that turns out to be, anyone? 7.1. So this is 7.1 volts across there, plus or minus. I now would like to go to you and say solve for the current. I'm going to use my buddy, V equals IR. I'm using my new numbers now. And what I have is V is equal to IR. My voltage was 7.1 equals the current I'm trying to solve times 150. And I want to solve for I. So that's 7.1 over 150. I go to my little buddy and I say, all right, what do you got for me? Fire up my calculator, and I say 7.1 divided by 150, it's 47 milliamps, okay? So this is equal to 0.4 or 0.047 amps. We don't talk like that. We say 47 milliamps, okay? All righty. Now, let's see if we can reduplicate that. So I have here a circuit which is a 9 volter going into 150 ohmer, and I want to see if I'm even close. So the first thing I want to do, I haven't even put the diode in, I want to make sure that this is the right value resistor. So I'm going to measure it really quick and say, is it 149? That's about 150. Okay, does everybody see that? Almost. So it's 150. Life is good. All right. Now I'm going to put the diode in. And I want to match this. I take the long guy as the anode, and then I'm going to pop it in there. And then I got my negative terminal and my battery right here. I jumpered it over here. I'm going to put it, it's on. Ow! It's burning me. No, it's not. It's not burning me. Do you see that it turned on? Life is good. Okay, I can prove that I'm actually powering it. So it's off, it's on, it's off, it's on. Magic. All right. Now I'm curious about the following. I'm going to measure some voltages around this puppy. First thing I'm going to do is I'm going to measure the voltage that's coming out of my battery. So I'm going to go from this terminal to that terminal, and what do I got? This crappy 8.55 volt battery! I bought a 9! That's all right. That's all right. We know that this is how it works. We do the calculations based on ideal, but we have to measure it and figure out what the actual values are. Now, I'm going to ask you, what do you think is across the diode? Oh my goodness, 1.9! What do you think's across the resistor? Whatever's left. It was supposed to be 7.1, but my battery's a little low, so it's whatever's left. Now I ask you, is the current going to be about 47 milliamps? Probably. Let's go ahead and measure current. So I'm going to take this voltmeter and I'm going to change it into current mode. So I move the lead over there. I'm going to go back to current with a line, straight line. And I'm going to say it's no more than 200 milli. And so I have to break the circuit. And I know that when I measure current, I go in line with it. It's cooled with a LED because if you touch it and it turns on, that's showing you that it's actually conducting. And look at what I got, 44.8 milliamps. That's close to my 47. Why isn't it just exactly the same? It's not that dang battery. That dang battery. Okay, okay. So we proved it to ourselves. We feel so good. We're just going to leave that thing on there. How's that feeling? How's that feeling? It's pretty good. It's pretty good. So then I ask, so when you go into lab tomorrow, we said we'd come back to this. Here is the circuit you're going to build. It looks exactly like what I just built. They are going to give you this. they are going to tell you that the turn-on voltage is 2 volts. That's the forward voltage. These things are called different terms. You just get used to all the different names for them. It's 2 volts, okay? You're going to fill out this monster table, okay? Monster table. Look at this. If the voltage source is negative 2 volts, is the diode on or off? Off. So you're going to come over here and the current is 0. Let's just do the currents for a second. What if it's 0 volt? What's the current? It's off, it's 0. What if it's 0.4? 0, 1, 0, 1.5. 2. This is where it turns on, but there's nothing left for the resistor, so it leaves it at 0, so that's at 0. From here on out, all you do is you take the excess above 2, put it across that resistor, and you calculate the current. The only tricky one on here, and I don't know why I put this here, was negative 2. Where's that negative 2 going to go? The only place it can go is across the diode. It's negative 2. There's still no current flowing. It's just to illustrate that you can go wacky and there's no current flowing. Okay? Then you're going to build that and you're going to measure it. We got 2 minutes left, and I say to you, this is your homework. Oh my God! Look at this! I got 2 loops, 3 if you're squinting. I got 3 resistors. And the forward voltage of the diode is 0.7. What are we going to do? Oh my goodness. Holy nuggets. You are going to have to use your KVL, KCL, Ohm's law knowledge and your new knowledge about a diode using the constant voltage model. You have to have at least 0.7 across it for it to turn on, then current will flow, but from then on out, it clamps at 0.7. Here, we have 60 seconds left. I want you to think about something. What is the voltage source when this turns on? Think about how crazy this is. If this turned on, just at the moment it turned on, what's the voltage across it? 0.7. Is any current flowing? That means no current is flowing through R3, right? That means by KVL, this is where the 0.7 is. So you've got 0.7 there, 0 there. If you do KVL, this is 0.7. Can you use Ohm's law to solve for this current right here, knowing that 0.7 is across the resistor where I give you the value? Yes. Now guess what? You can figure out this current doesn't come from here, it comes from over here. So now I2 is this loop, I1 is equal to I2. You can now solve for the voltage V1. You then take V1 plus V2, and that is the voltage at which it turns on. Look at how crazy that was. You guys all collectively pissed your pants when I showed you this, and then we walked through it, and you're like, oh, easy. All right, so again, as you walk out, I walk you through every step of the way, so just read the instructions and go through it step by step. All right, we'll see you in lab.